Hi there, my name is Charles Siba. Welcome to the second presentation on finding eigenvectors. Just recapping, previously we looked at this equation and saw how it generates the system of equation, which we summarize this way. And then we took an example of 2 by 2 and we got two eigenvalues here, minus 1, minus that. And at this stage, I'll remind you that we talked about multiplicity of eigenvalues. In this case, eigenvalues which are not repeated like these ones are going to be called simple eigenvalues. Otherwise, if it's repeated, they're going to be of, say, multiplicity 2, 3, and so on. Then we went through solving this equation, system of equations, to get the eigenvectors. One which was minus 2, 1 multiplied by a scalar, remembering that if we find a single eigenvector, the scalar multiple of it is also an eigenvector, and then the second vector gave us this kind of vector. Now what we're going to do, we're going to proceed to getting an example of a 3 by 3 matrix and computing eigenvectors. At this stage, I'm going to avoid the tedious calculation of finding eigenvalues by taking a matrix which we've already worked with and we know the eigenvalues, and then just engage with the process of finding the eigenvector. Okay, one such example of a matrix for which we determined eigenvalues was matrix A, which is 1, 2, 0, 1 minus 1, minus 1, 1, 3, 2, minus 2. And the eigenvectors were simple eigenvalues were simple eigenvalues, minus 2, minus 1, and 1. Now in this case, we're dealing with the eigenvalues which come at a multiplicity of 1. Now there's no eigenvalue which is repeated. Now let's start by saying for lambda 1 equals to minus 2. Obviously, if you've forgotten the process of finding these values, you just need to go back to the previous slides on finding eigenvalues and just revise and come back and do this and get the eigenvectors. So in this case, we're going to now find eigenvector 1. Now, seeing that we've got to now have the form of the second vector is E1, 1, E1, 2, E1, 3, that. Now, having this form of a vector, then let's take back to that expression which says A minus lambda I multiplied by the vector, in this case A1, will give us 0. Now you should remember this will take us to a system of linear equation, 3 unknowns, E11, E12, E13. So what we're going to do now, we've got to have our matrix here. I'm going to now be quick on this one because I think we've discussed it several times. Now we're going to have your 1 minus lambda, and the lambda is minus 2. So it's going to have here, we're going to have 1 minus 2, which is going to be 3, 2, 0. And next, we're going to have minus 1. Then we're going to have your minus 1 minus 2, which will be 2 minus 1, which we're going to have here is 1. And then we've got 1. Then 3, 2, 2 minus 2, that will give us 0. And we are rewriting this expression, and then here we got E11, E12, E13. Then this is equal to 0 vector in R3, then 0, 0, 0, and this is equivalent to a linear system of equation, which is going to be 3 E11 plus 2 E12 plus 0 E13 equals to 0. I'm just writing that for completeness so you can see what happens. Then this is minus E11 plus E11 plus E11 equals to 0. Sorry, E12, E13. That's a bit clumsy there. Let's correct this. E12, E13. And lastly, we got 3 E11 plus 2 E plus 2 E12 plus 0 E13 equals to 0. So equation 1, equation 2, and equation 3. Now, normally this equation being a equation of three unknowns, three equations, three unknowns, we can use any methods of solving linear equations we know. But in this case, this one is a simple one. We don't even need to use a method of elimination, whatever. We can just look at equation 1 and 2. It's exactly the same equation. So what we're going to do here, we're going to express E11 in terms of E12. Then we'll get E3 E11 plus 2 E12. That is from equation 1 and or 3. Then equals to 0. This tells us that E11 is equals to minus 2 over 3 E12. Now we need to get E13. Then what we can do, we can substitute E11 in next equation there. We have minus brackets minus 2 over 3 E12 plus 3 over 3 E12, that is 1 E12 equals to minus E13, that is from equation 2. Then what we have here, we're going to have adding these two with 5 over 3 E12 equals to E1 minus E13, which you can say therefore E13 is equals to 5 over 2, sorry, over 3, 5 over 3 E1, 2 with a minus sign there. So what we have here, we have that our E11 depends on E12, E13 depends on E12. So we can freely choose E12. So choosing freely E12, we can do this now, build our vector E1. Let's say I choose E12 to be 3. So I put here E12 be 3. Then if my E12 is 3, my E11 is minus 2. And my E13 is minus 5. This is one approach you can use to find your vectors, but you can also use the usual ways of solving linear equations. When I'm talking about usual ways, you can use the method of elimination, Cramer's rule, or any other. Then now this is my representative. This is our representative vector. Then you can say alpha is scalar and multiply it, and they say alpha is a scalar. So what have we done there? We found our eigenvector corresponding to lambda equals to minus 2. Now at this stage, we need to proceed and find eigenvector for lambda equals to, our eigenvectors were minus 2, minus 1. So now I'm not going to leave out minus 1 for you to do at home as your homework. Let's discuss when lambda is equals to 1. And let's go. Okay, for each vector, or for each eigenvalue we discuss, we mustn't lose sight of the original matrix which you're given because it's important. Then let's take now our expression A minus 1 times the identity. In this case, it's going to be the identity. You can just write here I multiplied by the non-eigenvalue 3, which we're looking for. This will give us a 0 vector. So doing this kind of calculation along the, especially the entries here involves, the calculation only involves the elements, the entries on the along the principal diagonal. We're going to have 1 minus 1, which will give us 0, 2, 0. Then minus 1, and 1 minus 1, we're going to have here minus 2, 1, 3, 2, and then minus 2 minus 1, minus 3. Our non-vector, 3-component vector E31, E32, E33, then equals to 0 vector. Right. So this again is going to give us a system of equation which is going to be 0 E11 plus 2, sorry, E31 plus 2 E32 plus 0 E33 equals to 0, then minus E31 minus 2E32 plus E33 equals to 0, and 3E31 plus 2E32 minus 3E33 equals to 0. So this is our system of three equations, three unknown to solve. Now, clearly from equation 1, we have 2E32 equals to 0. But we know that if two numbers are multiplying each other equal to 0, one of them should be 0. So in this case, you can say, therefore, E32 is equals to 0. Now, if E32 is equal to 0, in equation number 2, from equation 2, we have minus E31 plus E33 equals to 0, which is equivalent to saying E31 is equals to E33. So in this case now, we are ready to build our vector. What we can do is we can now say our eigenvector number 3 has got the middle component being 0, the first and the last component equal. Then you can conveniently choose the 1 and the 1. Somebody else could have chosen 2 and the 2. That's your choice. So then, let's say this is equal to gamma multiplied by that, where gamma is a scalar. So at this point, we found two vectors for lambda equals 2 minus 5 minus 2, and lambda equals to 1. And I left the other eigenvector lambda equals to minus 1 to do it for your practice. So now, this example, 7 example of finding eigenvectors for simple eigenvalues, our non-repeated eigenvalues. Our next example will involve 3 by 3 with repeated eigenvalues. For now, thank you for listening.